So in the previous lecture, we defined what we call determinants, and we tried to find ways on how to determine determinants of n by n matrices. So for this lecture, we will give some properties of determinants. So first, we have the following. Let A be an n by n matrix and let K be a scalar. Then the determinant of Ka, this is equal to K to the n times the determinant of A. So here, Ka, we are multiplying all the entries of A by that scalar K. Okay, so if we want to find the determinant of Ka, we just have to factor that K and raise it to power n, power size of the matrix, and then multiply that to the determinant of A. So for example, we have the following. So we have a 4 by 4 matrix, and all the entries of this 4 by 4 matrix are multiplied by K. So if we want to get the determinant of this is equal to K to the 4 times the determinant of the 4 by 4 matrix with entries A11, A12, A13, A14 until etc. until we have A44. So again, if the matrix A is multiplied by a scalar K, it means that the K is being multiplied to all the entries of A. So the determinant of Ka equals K to the n determinant of A. Now, we don't have this property. So we have the warning that determinant of A plus B is not always equal to the determinant of A plus the determinant of B. So this means we cannot just distribute the determinant over sum of matrices. So for example, let A be equal to this 2 by 2 matrix, let B be equal to this 2 by 2 matrix. Then if we want to find the determinant of A, since this is just a 2 by 2 matrix, okay, we can easily calculate that it is equal to 1. So 1 times 1 minus 1 times 0. So 1 minus 0, which is equal to 1. And the determinant of B, since these are proportional rows, 1, 1, 1, 1. So if we calculate the determinant, it will give us 0. Okay, but if we want to get the determinant of A plus B, so A plus B, so if we add A and B here, we will have what? The determinant of the matrix. So 1, so 1 plus 1 in here, okay, we will have 2, and then 0 plus 1 in here, we will get 1. And then for the other two entries, we also get 2. So if we get the determinant of this matrix, we will obtain 2 times 2, that's 4 minus 2. This is equal to 2. And notice, determinant of A plus the determinant of B, it is equal to 1. And they are not equal now. Okay? So in general, if you have the sum of matrices, you get the determinant of that. It is not equal to the determinant of A plus determinant of B. Okay? However, suppose we have these three matrices A, B, and C, and these three matrices have the same sizes n by n, and all of them have the same entries except only in a single row. Okay, except only on a single row, say row R. Okay, and then suppose the rth row of C can be obtained by adding the corresponding entries of rth rows of A and B. Okay, so all of the entries of A, B, and C, they are all the same except for the rth row, okay? And then the rth row of C is equal to the rth row of A plus the rth row of B. Then the determinant of C, it is equal to the determinant of A plus determinant of B. Okay, so determinant of C equals determinant of A plus determinant of B. Okay, and if we replace row by columns, we still get the same result. So for example, so we want to find the determinant of this matrix here. And on the third row, I wrote 1 plus 0, 2 plus 3, and 6 minus 2. Okay, so the theorem says this determinant here is equal to the following. So the first two rows, okay, first two rows, they are the same on the first two rows of the original matrix on the left. Also on this part, okay, first two rows, the same as the first two rows of the matrix on the left, but the third row, okay, so I get the first adjoint 1, 2, and 6. So this is 1, 2, and 6. It is on this part. And the second adjoint 2, 3, and minus 2. I put it on the third row of the other matrix. So this theorem tells us that this equation here is indeed correct. So try to verify using our formula or methods that the determinant of this is equal to the determinant of this plus the determinant of this. So you can verify that one. It will be a good practice. Okay. Next, let B be an n by n matrix and let E be an n by n elementary matrix. So take note, elementary matrix, it's a matrix obtained by applying a single elementary row operation on the identity A matrix. Then, the determinant of the product EB. Remember how to obtain the product EB if E is an elementary matrix. We want to get how or the row operation used in order to obtain the matrix E, and then you will use that same row operation to the matrix B to obtain the product EB. Okay? But the theorem tells us the product EB is equal, or the determinant of the product EB equals the determinant of E times the determinant of B. And recall also that the determinant of E only has three cases. So either it's positive 1, negative 1, or some scalar K. Okay? So positive 1, negative 1, or some scalar K. Okay? Coming from this, okay, we can prove that the determinant of a square matrix A is invertible if and only if the determinant of A is not equal to 0. Okay, so we can use this result here in order to prove this theorem. So this is an if and only if statement. So this has two ways. Okay, the first one is A invertible. Okay, invertible. This implies that determinant of A is not equal to 0. Okay, this is the first statement there. And the second statement is that determinant of A not equal to 0. This implies that A is invertible. Okay, so if and only if statement, two ways. So A invertible implies determinant of A not equal to 0. And also, determinant of A not equal to 0 implies A is invertible. Okay? Now, combining these two results, we will obtain the following. Let A and B be n by n matrices. Then, the determinant of the product AB is equal to the product of the determinants of A times determinant of B. Okay? So, we don't have a generalization for, or we don't have a general statement regarding determinants of sum of matrices, but for determinant of product of matrices, we have, okay, determinant of AB equals determinant of A times the determinant of B. So for example, we have these matrices, 3, 3, negative 1, 1, 1 for matrix A, and for matrix B, we have 1, 5, negative 2, 6. So let us first get the determinant of A. Determinant of A, this is equal to 3 minus negative 1. So this is equal to 4. Determinant of B, this is equal to 6 minus negative 10. So this is equal to 16. Okay? So according to this theorem, determinant of AB, okay, this is equal to determinant of A times determinant of B, and this is equal to 4 times 16, which is equal to 64. Okay? Let us verify this. Let us multiply out A and B. Okay? So the matrix A, it's 3, negative 1, 1, 1. And then we have the matrix B, 1, 5, negative 2, 6. So if we multiply them, we will have 3 times 1, that's 3. And then negative 1 times negative 2, so plus 2. Okay. Then for this entry, we have we have 3 times 5. We have 15. Negative 1 times 6, so minus 6. And then for this entry here, 3 times, 1 times 1, that's 1. And then 1 times negative 2, so that's minus 2. And finally, for the entry here, we have 1 times 5, that's 5, plus 1 times 6, that's 6. So if we simplify this, we will have 5, 9, negative 1, 11. And clearly, if we use now this formula here, okay, determinant of AB, this is equal to 5 times 11, that's 55, minus 9 times negative 1, that's negative 9. This is indeed 64. So same as this product here. Okay. Next. If A is invertible, then we can get the determinant of A inverse, and the determinant of A inverse is equal to 1 over determinant of A. So using this formula, it means that we don't have to get the inverse of A to find the determinant of that A inverse. We only need to know the determinant of A. So determinant of A inverse equals 1 over determinant of A. Okay? Now, recall we defined what we call the cofactor of the matrix A. So cofactor of the entry Aij, which is denoted by Cij. Okay? So what we're going to do is to put those numbers, Cij's, into a matrix. And we have this C11, C12, C1n until we have Cn1, Cn2, Cnn. We call this matrix the matrix of cofactors from A. Now, the transpose of this matrix is called adjoint of A. And we denote this by ADJ or adj of A. So in some references, we call this the adjugate of A. But in this reference, we call this adjoint of A. And the adjoint of A may be different from other books. So for our course, the adjoint of A will be defined this way. Okay? We have the matrix of cofactors, and then we get the transpose of that. That will be the adjoint of A. Okay? So for example, let's have this matrix here, and we want to find the adjoint of this matrix. So first, let's have C11. C11, by definition, it's negative 1 raised to 1 plus 1, and then determinant of the matrix obtained by deleting the first here, the first row, and the first column. So this is 2, 6, 2, 6, but these rows are proportional, so this is just equal to 0. Okay? Now C12, this is equal to negative 1, 1 plus 2, and then we want to get the determinant of the matrix obtained by deleting the first row, okay, first row and the second column. So we have negative 5, 6. Let me write that properly. So negative 5, 6, and then 1, 6. So if you get the determinant, this is negative 30 minus 6. So this is equal to negative 36. Let us continue. We have C13. This is negative 1. Sorry, we have negative 1 raised to 1 plus 2. So we still need to get the negative outside, because negative 1 raised to 3, that's negative 1. So I have a negative outside. So let me write this properly. So I have that negative outside, and therefore C12 is actually positive 36. Okay. Moving on, we have C13. It's negative 1 raised to 3 times the determinant of the matrix obtained by deleting the first row and the third column. First row, third column. So determinant of negative 5, 2, 1, 2. And negative 1 raised to the power 4, that's positive 1. So we will have negative 10 minus 2. This is equal to negative 12. Now we have C21. C21. We have negative 1 raised to 2 plus 1. Determinant. So for C21, we remove the second row and the first column. Okay. So we will have 1, negative 4, 2, 6. So if you get the determinant times this negative 1 raised to 3, so we have negative of, we have here 6, and minus 2 times negative 4, so 6 plus 8. This is equal to negative 14. Okay. C22, C22, negative 1 raised to 2 plus 2, and determinant of the matrix obtained by deleting the second row and second column. So we will get here 2, negative 4, 1, 6. This is equal to, so negative 1 raised to 4, that's positive 1. So we'll just have 12 minus negative 4. So I will just write 12 plus 4, and this is equal to 16. Okay. And then C23, we have negative 1 raised to 2 plus 3, determinant. So we remove second row and third column. So second row and third column. So determinant of the matrix 2, 2, 1, 1, 2. and negative 1 raised to 2 plus 3, that's negative 1. And then we have 2 times 2, that's 4 minus 1. So this is equal to negative 3. Okay, let us continue now to the third row. We have C31. This is equal to negative 1 raised to 3 plus 1, determinant of the submatrix obtained by removing the third row and first column. So we will have the determinant of 1, negative 4, 2, 6. Okay, and negative 1 raised to 3 plus 1, that's positive 1. So below here we have 6. We have 6 minus negative 8. So plus 8. This is equal to 14. 2 entries left. We have C3, 2. We have negative 1 raised to 3 plus 2 determinant. So determinant of the submatrix obtained by removing the third row and second column. Okay, so we will have 2, negative 4, negative 5, 6. So this is equal to negative 1 raised to 3 plus 2. So that's negative there. Quantity. Okay, quantity, we have 12 minus 20. So this is negative 8, and then there's a negative outside. We will have positive 8. And finally, the last entry here, you have C33. Okay, this is equal to negative 1 raised to 3 plus 3 times the determinant of the matrix obtained by removing the third row and the third column. So third row, third column. So here we will have 2, 1, negative 5, 2 here, and negative 1 raised to 3 plus 3, that's positive 1. And then we will have 4 minus negative 5. So 4 plus 5, this is equal to 9. Okay, so I think I forgot to write the 2 plus 2 in here, but anyway, it's still the same there. Okay, therefore, the adjoint of the matrix. So if I'm going to label this as matrix A, then the adjoint of the matrix, okay, so in here I will already write the actual adjoint, okay, the actual adjoint, meaning the transpose of the cofactors. So meaning the first subscript of C will refer to the column of the adjoint, and the second subscript of C will refer to the rows of the adjoint. So in here I have 0, this is C11, this is 36, this is C12, and then C13, negative 12, okay? And then for the other entries, we have 2, 1, 2, 2, and 2, 3. We have negative 14, 16, and negative 3, 16, and negative 3. And for the last one, we have, for the last column, we have 14, 8, and then 9. So this will be the adjoint of the matrix A. Okay? Now, is there any other shortcut for the determining of the adjoint? The answer is yes. But how do we do that? So using this theorem, okay? So if A is invertible, the inverse of A is equal to 1 over determinant of A times the adjoint of A, okay? So somehow, if you know the inverse of A, then you can get the adjoint of A by multiplying the inverse of A by the determinant of A. On the other hand, you can easily get the adjoint or the inverse of the matrix A if you already know the adjoint of A. Okay? So example, find the inverse of this matrix. This is the same matrix as here. 2, 1, negative 4, negative 5, 2, 6, 1, 2, 6. So 2, 1, negative 4, negative 5, 2, 6, 1, 2, 6. So we have the adjoint. Okay? What's left to do is to get the determinant of A, and therefore we will be able to find the inverse of A. And to get the determinant of A, so we can use one of the methods that we know. What we can do is to augment, okay? Let me just augment it here. Augment the first two columns of A. So I have 2, negative 5, 1, and then 1, 2, 2. And then we get this guy here. We multiply these guys here. We multiply these guys here. And we also multiply these guys here. Okay, and then we will add them. So 2 times 2 times 6, that's 24. 1 times 6 times 1, that's 6. Negative 4 times negative 5 times 2, that's positive 40. Okay, positive 40. And for the other guys, so we multiply these entries here, we multiply these entries here, and we multiply these entries here, and then we will subtract them to the sum. So here, 1 times 2 times negative 4, that's negative 8. 2 times 6 times 2, that's 24. And then 6 times negative 5 times 1, that's negative 30. Okay, so determinant of that matrix. Okay, I think we labeled that A from the previous slide. Yes, we labeled that A, so let's just use A also here. So determinant of the matrix A, this is equal to 24 plus 6 plus 40, then minus, we have minus 8 plus 24 minus 30. So if we add them together, what are we getting here? We have 46 plus 38. Okay, 46 plus 38, that's equal to 84. So try to add them. You have 26 or 24 plus 6 plus 40, and then minus 8 plus 24 minus 30. Okay, so if you add them, you will get 84. And therefore A inverse, this is equal to 1 over 84 times the adjoint that we obtained from the previous slide. So let me check that. So 0, 36, negative 12, 0, oops, let me write it, 0, 36, 36, negative 12, negative 14, 16, 3, negative 14, 16, negative 3. Did I write that correctly? And then 14, 8, 9. Then we have 14, 8, 9. Okay, so this is the inverse of A. So all we need to do is to multiply this 84 to all the entries of this matrix here. Okay, so you can verify using inversion algorithm on this matrix, okay, to find the inverse of A, but you should get the same uh, values or matrix in here, provided, of course, this computation is correct. Okay, so I want to end this lecture, okay, by recalling the equivalent matrix, the equivalent statements that we have, and then we will add another statement here. So we already have 6 statements here, but all of these statements, okay, they are equivalent to the fact that determinant of A is not equal to 0. So in the previous theorem, just several slides ago, we have A invertible if and only if determinant of A is not equal to 0. But this statement here is true if and only if statement D is true, if and only if statement C is true, if and only if statement D is true, if and only if statement E is true, if and only if F is true. So all of them will be true, okay, if one of them is true, or all of them will be false if one of them is false. Okay, so that's the end of the discussion, and thank you for staying.